Students lose so many marks on CSEC math relations, evaluating, and inverses because of this one misunderstanding.
Hey everyone, and welcome to this explainer. I'm absolutely thrilled to have you hanging out with us today. Look, if you've ever stared at coordinate geometry and algebraic functions and felt like you're looking at some sort of broken, overly complicated engine, you are completely in the right place. Today, we're going to demystify all of that. And we're going to do it using a really simple, but honestly, super powerful metaphor, the function machine. By the end of our time together, you're going to see exactly how mathematical inputs and outputs connect, how you can actually run quality control on these machines, and most importantly, how to throw them entirely in reverse. So let's just dive right in. Here's our quick roadmap for today. First up, we've got relations versus functions. Number 2 is the vertical line test. Third, evaluating the function machine. Fourth, avoiding common exam errors. And finally, deriving inverse functions. All right, let's hit section 1, relations versus functions. Now, what's really fascinating here is just how broad the concept of a relation actually is. Think of a relation as basically any connection or mapping between two sets of numbers. We call the set of inputs the domain, and those outputs, that's your range. You'll see these connections drawn out in a bunch of ways, like arrow diagrams, or written as ordered pairs with your x and y coordinates, or even just mapped out in tables and graphs. If there's any sort of mathematical link between two sets of data, boom, you've got a relation. It's really the big umbrella term for all of these connections. But here's where we get a bit more specific. A function is a highly specialized relation. Think of it as our function machine. For any machine to actually be reliable and useful to us, it needs to be totally predictable, right? When an input, let's just call it x, enters the machine, a very specific formula or rule gets applied. To be classified as a true function, that one input must lead to exactly one output. You push a specific button, you get one specific result, every single time. So the absolutely crucial takeaway here is this golden rule. Every function is a relation, but not every relation is a function. I really want you to mentally highlight this because it's such a foundational concept, especially when you're taking on CSEC mathematics. A relation, it can be totally chaotic, but a function, it plays by strict rules. It's either a one-to-one mapping or a many-to-one mapping, but no matter what, every single input has its own specific single output. So how do we spot the fakes? How do you look at a relation and know it's completely failing to be a function? Well, you look for what I like to call greedy inputs. Imagine an arrow diagram where person A is our input. If person A points to two totally different outputs, say phone number 1 and phone number 2, that's a one-to-many mapping. One input is trying to grab multiple outputs. That completely breaks the machine. You can spot this same thing in ordered pairs too. If you see repeating x values paired up with different y values, like the coordinate 2, 5 and the coordinate 2, 7, that input of 2 is literally giving you two completely different results. It's absolutely a relation, sure, but it completely fails the test to be a function. Okay, moving right along to section 2, the vertical line test. Now that we've tackled the raw numbers and diagrams, let's shift gears and get visual. The absolute easiest way to run quality control on a graph is the vertical line test. It's the go-to graphical method for spotting a broken function machine. The rule is incredibly simple. If you can draw a perfectly straight vertical line literally anywhere through a graph, and that line intersects your drawn curve at more than one point, then the relation you're looking at is definitely not a function. Let's actually picture what failing that test looks like. Think of a perfect circle drawn right on a graph, or say a sideways parabola opening up to the right. If you drop a vertical line straight down through the middle of that circle, or right through that sideways parabola, your vertical line is going to chop right through the top of the curve and the bottom of the curve. It hits it twice. So what does that actually mean mathematically? It means a single x value on your horizontal axis is corresponding to multiple y values on the vertical axis. Your input is being greedy again. So yeah, it's a relation, but no way is it a function. Which brings us to section 3, evaluating the function machine. All right, we know how to identify a working machine. Now we're actually going to physically operate it. This is basically a plug-and-play process, but we have to be super meticulous here. Let's evaluate a function step by step together. Our source example gives us the function g of x, which equals the fraction 7x minus 3 all over 5. And the question is asking us to evaluate g of negative 6. Step 1 is the substitution rule. We swap out every single x with a negative 6, and you must, I repeat, must, put that negative 6 inside brackets. Step 2, we simplify the top row, the numerator, strictly using BODMAS. We treat that entire top part as if it's locked in its own brackets. So we multiply first. 7 times -6 gives us -42. Then we subtract the 3. -42 minus 3 gives us -45. Step 3 is easy. Our denominator is already simplified. It's just the number 5. And step 4, the final division. We divide our fully simplified numerator by our simplified denominator. So that's -45 divided by +5. And the machine spits out its output. The final correct answer is -9. Now, here's what's really cool about this. You can use a super quick mental math check to verify your work. You knew the top of your fraction was a fairly large negative number, right, around -45, and you were dividing it by a small positive number, 5. Therefore, your answer just logically has to be a smaller negative integer. -9 fits that perfectly. Always, always do that quick mental check. All right, on to section 4, avoiding common exam errors. Okay, lean in for this part because I'm going to share some serious insider secrets with you right now. These are the cheat codes for avoiding the totally common traps that catch out so many students on exams. A massive life hack for your non-programmable calculators is something called the bracket trick. When you're dealing with fraction expressions, a calculator doesn't automatically magically know what the top of the fraction is versus the bottom. If you just casually type 7 times -6 minus 3 divided by 5, the calculator is only going to divide that very last number, the 3, by the 5. It completely ruins the whole equation. The absolute right way to do this is to wrap brackets around the entire numerator before you even think about hitting that divide button. Beyond just calculator inputs, let's run through a quick troubleshooting checklist for common errors. First up, premature division. That's trying to divide before the entire top row is fully 100% simplified. Second, bypassing BODMAS. Don't ever subtract your numbers before you do your multiplication. Just don't do it. Third, sign errors. This one is huge, folks. Remember your directed numbers. A positive times a negative is a negative. Don't accidentally calculate 7 times -6 as +42. That happens all the time. And finally, always use brackets when you substitute. Oh, and a massive, massive exam tip. Even if your final answer ends up being totally wrong, show your steps. Mark schemes will actually award you partial method marks if you just show your simplified numerator and denominator separately. And finally, section 5, deriving inverse functions. So we are now moving to the ultimate mastery step in this explainer. You know exactly how the machine works forward. But what if you already know the output? And you need to find a mathematical rule that completely undoes all the operations of the original function to get you right back to your starting input. Think about it. If a function doubles a number, its inverse would have it. We denote this special relationship with a little -1, as in f to the power of -1 of x. Let's ground this rather abstract concept for a second. Think of your original function as the specific route you walk every day from your home to your school. The inverse function? That's simply the route from your school right back home. It's the exact same path, just processed in completely the reverse direction. And geometrically, if you were to map this out on a graph, the inverse of a function is a perfect visual reflection of the original function directly across the diagonal line y equals x. They are perfectly, beautifully balanced. So how do we actually derive this algebraically? Let's walk through this 5-step reversal algorithm using a great example from our sources. F of x equals 2x minus 1 all over x plus 3. Step 1, we set the whole expression up by replacing f of x with our inverse symbol, and we set that whole thing equal to x. So we've got 2 times the inverse minus 1 over the inverse plus 3 equals x. Step 2, we've got to get rid of that fraction, so we multiply both sides by the denominator. That leaves us with 2 times the inverse minus 1 equals x times the inverse plus 3. Step 3, we expand that out, and we group all the inverse terms on one side of the equal sign, moving our x terms to the other side. You really got to be careful with your algebraic signs here. Step 4, now we've got multiple inverse terms sitting on one side, so we factor out the inverse to totally isolate it. Step 5, finally, we just divide to solve for our final expression. If you follow those exact steps, the inverse function ends up being 3x plus 1 all over 2 minus x. Make sure you show every single one of those rearrangement steps to guarantee you get all your method marks. And wow, that brings us to the very end of our explainer. I want to leave you with this final kind of mind-blowing thought. Math is really just a series of reversible processes.
Once you know how the function machine connects your inputs to your outputs, how to test it, how to operate it safely with those correct bracket inputs, and how to run the algebra in total reverse, you're honestly no longer just solving math problems. You are entirely commanding the machine. I really hope this breakdown has completely demystified these concepts for you. Keep practicing those algebraic steps. Seriously, watch your negative signs, and I will see you in the next explainer.
As always, the link for this study tool is in the description below. Let me know what you think in the comments.